Thanks, Tiana, for the introduction. Before we start, multi-choice question. Out of the four photos on the screen, can you tell which one is real? I asked Agent Arena to generate some photos of dogs inside our office. So for folks over here, it's not hard to tell. Like photo C is like the real dog, the Belka and Strelka, who went to the space, like the first creature who went to the space. They're the real dogs. And the other one are the dogs that are generated by Agent Arena in our office. Currently, we're already living in a world where we're surrounded by synthesized images, synthesized content online, and synthesized data. So, well, maybe someday synthesized human being or person will no longer be a future. Well, in a world like this, we couldn't help but ask, is the question still about what is real and what is fake? Or I feel like more important question would be, how close are we to the real world? If we want to build something based on synthesized data or synthetic data, how close is it to the reality and how much trust can we put in it? Especially under the scenario where there's no ground truth to check against. So our talk today is going to answer this question. The title of the talk is Valid Inference with Synthetic Data via Task Exchangeability. So this is a joint work with our amazing Tiana, who's also now a professor at a statistics department at Stanford. So let's set the scene first. Well, as it's no longer a surprise for all of us that like synthetic data is everywhere. It's already integrated into part of the production line. There are several fields that we can name. One of the field that we are most familiar with, which is the as a judge, the AI evaluation field, where we can use AutoRater AI models or a reward model that we train to grade other AI models. We can create the battles between them so that we can collect the evaluation data or the ratings between them even before the human raters kick in. Well, in the social science field, social scientists are using silicon samples, which is basically asking the LLMs to role-play a survey respondents from the demographic profiles that they collected from the population so that they can conduct pilot studies without fielding a survey, which will cost much more time and money. Well, for the science, we have all heard of that. Like, generative models are producing synthetic protein structures, medical records, behavioral data, etc., that will be input into the scientific discovery. Well, also, it's not hard to guess that for the physical AI and self-driving, people are using simulators to generate the rare and dangerous event where crashes, edge cases that should be learned by the car, learned by the robotics, but it's really hard or it's almost impossible to be staged in the real world. So all of this deployment just happened for one single reason, because the synthetic data is cheap and fast and it scales. It's available for any task that you can describe in a prompt. And here are a few literature that I listed over here that support the ubiquity of synthetic data across social science, as a judge, a paper by Wei Lin before, and also use of synthetic data in the AI training itself, and also use of synthetic data in science. And this literature also gives us a more concrete clue of how cheap and fast are synthetic data. For example, for a public opinion survey that wants to recruit 1,500 representative respondents for data, if you rely on human data, then usually it would need weeks to field, and the cost is around 30 or 30,000. But with synthetic data, it's $15 within a minute. Well, also in AI training, if you're waiting for human votes to kick in to fine-tune your model, usually you need to wait days to weeks, and the costs that are reported in the literature are around 2,400. But with the synthetic data in human votes or AutoRater votes, the cost in money is 5 times cheaper within a minute, so that you can iterate on your model training within a minute. But it's just no surprise for us that nothing is perfect. Cheap doesn't mean it's actually correct. So all this literature has also revealed the systematic bias of synthetic data, where, for example, the judge shows that only 80% of the time the judge would agree with human, and also the rest of the 20% would be systematic bias that can hard to average out. And the trap over here is that cheapness is exactly the reason why there is no ground truth data to check against. So if we have the budget to collect all the real data, then we wouldn't be wanting to use the synthetic data at the very beginning. And because synthetic data is cheap, it is mostly used in the field where no ground truth data has been collected and to be checked against. And in that case, what can we do? Well, the first thing we can say about is something we cannot do. That is, pretending synthetic data is real really goes badly sometime. So this is an example of ANTS, American feeling thermometer question, where it is like collecting data from some partisan subgroup to survey on their feeling towards several rating groups in American. And 0 represents like they feel really cold towards this group, and 100 represents they feel really warm towards this group. And the synthetic respondents are generated by ChatGPT 3.5. And the cross represents the true mean, while the orange interval represents the naive synthetic only interval. So you can see that the synthetic only interval is narrow, it's tight, it's confident, but is almost never cover the truth. So it's confidently wrong. While the gray interval that we generated are wider. Honestly, it is indeed wider, but for most of the time, it covers the truth. So the rest of the talk will be about, how do we do that? And well, our method comes from a simple logic that there's nothing new under the sun. So even though for the new data that you want to overcome or you want to tackling into currently, you don't have enough like ground truth data, or even you don't have access to the ground truth data at all. But there are millions of like tasks that were conducted before under the similar context. For example, odor waves, odor surveys, odor questionnaires, odor models that were released. So for the historical data, we have both columns because we can also apply the same generator to run on the historical task. And the question becomes, a natural question becomes, for all these historical tasks that where we can have both access to the real data and the synthetic data, how can it bias valid inference on the new task where we only have synthetic data? And can it actually bias valid inference on the new task? And our answer is yes, under just one simple condition called Task Exchangeability. And later on, we will also introduce a variation of it that goes beyond this simple condition. So for folks that might be familiar about statistics or conformal prediction, that might heard of the exchangeability or might be familiar with the terminology of exchangeability. But for people who are not familiar with the term of like exchangeability, here is one line definition in natural language. We would say a sequence Z1 to Z5 or like Z1 to Zn random objects to be exchangeable if shuffling their order doesn't change its joint distribution. So it is not saying that all these random objects are independent or saying that they are a copy of each other, but instead it's just like saying from the point of view of joint distribution, changing their order doesn't change the joint distribution. Well, if I want to give a simpler example to help folks understand like what exchangeability means, I would like to take an example from the World Cup that had just happened. We know that at the final game of the World Cup, the Spain beat Argentina by 1-0. Well, for people that are more familiar with the soccer game, they would know that Ferran Torres was the one that scored the winner. But for someone like me that doesn't actually know enough about the soccer player,
for me, it doesn't actually matter who scored the goal or who put in the ball. Either it's like Z1 equals to 1 or Z4 equals 1, doesn't matter. Shuffle the order between the players in the front line doesn't change the final result that Spain scored the 1 goal that beat the Argentina. So the methodology under exchangeability is just the name on the goal carries no information about the result. And based on the exchangeability, there's a consequence that we will use throughout this work. Throughout this work. So in an exchangeable sequence, the new items rank among the all items that are existed is uniform. So when a new item comes in, it's equally likely to be the largest or the strongest or the smallest, anywhere in between. So this is a single fact that turns historical quantiles into some guarantee that we can draw on the new task that we are facing today. Well, here's a more concrete example of when tasks can be exchangeable. So even though all the tasks might be correlated throughout the history, but there is usually there is a shared environment. Either it's a survey program that generates all this questionnaire, or it's a model family or a lab that produces all these models. Then given that environment, if the tasks are drawn independently, identically from the underlying environment, then we can view the task as exchangeable. Well, note that this is a relaxation to the independent, because the models from the lab can be correlated to each other, they share the same pattern, but the thing is, because they are drawn in the same way, relabeling them or shuffling their order changes almost nothing. So that is what exchangeability is talking about. Well, one honest caveat over here is that the symmetry between all these tasks will only break if you select the new task because it looks unusual. So if you just go hunting for the strongest model, or you go hunting for the weirdest task, then there's no guarantee for the exchangeability between the tasks, between the new task and the older task. So now that we have a more concrete idea about the concept of task exchangeability, let's be more precise about what a single task actually contains. And here, the key distinction is between the distribution and the data set. And that is something we're all quite familiar about. So there are 2 parallel worlds and 4 moves. In the real world, we always believe that for a single task, there is a ground truth distribution, but we cannot observe that. What we have in hand is always the data set that are believed to be drawn from the underlying true distribution. And based on the real data set that we drawn from the true distribution, we apply an estimator to the data set we have in hand. And it's called theta hat real. So theta hat real will be served as an approximation to the target of inference, theta real, which is the underlying feature of the underlying true distribution P real. Well, the synthetic world is basically just a mirror, where you have a generator in your hand, for example, the LLM, or for example, some later on we will show that how we generate synthetic data. Basically, you have a generator in hand. Given a task, you can sample mostly as much as synthetic data that you like under a budget constraint, but it will be a much looser budget constraint. And then based on the synthetic data, you can also apply the same estimator called theta hat synthetic. So that is something you can actually compute for the new tasks. And we believe that as long as we can draw enough synthetic data, the theta hat synthetic will be converged to the generator ground truth, or the generator feature that is called theta synthetic. So we use the delta to measure the gap between the real world and the synthetic world, which is the gap between the theta real and the theta synthetic. Well, one caveat is that in the real world, because we only have access to the data, although we're targeting at the gap between theta real and theta synthetic, we can only have access to the theta hat real and theta hat synthetic. So in the situation or in the scenario that we are targeting at, the S real or the data set real is never observed before the synthetic data. So that is the challenge for the whole story. After we set the notification for both the real world and the synthetic world, here's our formal assumption for the task exchangeability. So for each task, we define the task itself and also the real data that come along with it. And the task exchangeability is not only the exchangeability between the tasks, but also containing the exchangeability between the task data set pairs. So ST is each task real data set, and as new is the new data set that we never observe. But we assume that if we have any access to the new data set or the real data set for the new task, then it will be exchangeable among the historical tasks that we have already observed. And one consequence of the assumption that we hold is that not only the tasks themselves are exchangeable, but what's really useful is the gaps between the synthetic data and the real data are exchangeable among historical tasks and the new task. And the exchangeability what the exchangeability bias is that the gap for the new task will fall into the quantile that are formed based on the historical gaps with the confidence of 1 over over 1 minus alpha. So what this assumption says in plain words, that the tasks and their data sets are drawn from the common meta distribution, and the current task is not special at all. Well, what it doesn't say is that the tasks are identical or independent. The new task can always has correlation with a historical task. And also, what it doesn't say is that the generator can be arbitrarily biased, but the bias should be observed across different tasks, across historical tasks and the new task, so that we can infer about the gap from the historical task to the new task. And now, based on the assumption of like the task exchangeability, we are actually using the gap that are observed from the historical task to infer about the gap for the new task. So for the new task, we have access to the theta hat synthetic, which will approximate the theta synthetic that we believe, and we use the historical that task to calibrate on the gap between the theta synthetic and the theta real. And the theta hat real in the gray box is actually something that we never observe. And this is like restatement about the setting that we are caring about. And here comes the methodology. Basically, it's just 3 moves. So the first one is super easy. It's like having the synthetic data in hand. We form a naive confidence interval for the theta synthetic based on the number of like synthetic sample that we have. And the second one is for each historical task, we also apply the same data generator to the historical task to get not only ST, which is the real data, but also S tilde T, the synthetic data for the historical task. And then we form a confidence interval for the delta between the theta synthetic and the theta real for the older tasks or for the historical tasks. And after we form such confidence interval across all the historical tasks, meaning we have a lower bound for the delta and an upper bound for the delta for each historical task, we just draw the quantile from the lower bound and we draw the quantile for the upper bound with the confidence alpha 3. And then we use that quantile from the lower bound as the lower bound for the delta nu, and we use the quantile from the upper bound as the upper bound for the quantile as the upper bound for our delta nu. And in that case, we would just output a confidence interval based on first the lower bound that we formed for the theta synthetic, and then added up with the lower bound and the upper bound we formulated for the delta nu. And here, based on the 3 moves in this method, here is the theoretical guarantee that we have derived for the estimator and for the confidence interval that we generated based on adding up this two confidence interval. And the guarantee is basically reflects the three moves that we have, like in our methodology: alpha 1, alpha 2, and alpha 3. And alpha 1 is the noise in, or like the finite sample noise in the synthetic data itself. Alpha 2 is the limitation of the finite sample in the historical task. And alpha 3 is the exchangeability quantiles, or it measures how much confidence do we have about the new task or about the new gap based on the historical gap. Well, one caveat or one variation is that throughout this whole framework, we are always targeting at the theta real, which is something that's depending on the underlying distribution, but not the finite sample. But sometimes, if we want to make things easier, we might only want to care about, okay, what is the fitted finite sample Bradley-Terry score that are gonna be published on the leaderboard. If we do not care about the theta real, but instead we care about the theta hat real, then the thing can be easier. That is, we no longer need to formulate a confidence interval around theta synthetic, and also we no longer need a confidence interval for the gap between the real world and the synthetic world on the historical task. Instead, we can directly compute out what is the delta, the gap between the estimator that are formulated on the real data set and the synthetic data set. And we use that. We still built upon the assumption about exchangeability, and then the coverage would be two-sided. We would have confidence over 1 minus alpha, and also we would have confidence that are capped by 1 minus alpha plus just something that are going to be capped by the number of historical tasks that we have. So here, the one-line interval would just be adding up the quantile from the gaps from the historical task and the quantile from the gaps from the historical task to the synthetic estimate. So this is how we target at the finite sample shortcut. And this is something will be applied to our working example in our agent leaderboard that we're going to later show. So after we introduce our method, here are 3 case studies that shows the effectiveness of the method. So the first one is in social science. The second one is the one that we are most familiar with to predict a Bradley-Terry score based on AutoRater that we have trained as a reward model. And the third one is beyond LM versus human, and it is like a work in progress related to our agent leaderboard, especially with a focus on the steerability score on the agent leaderboard. So let's go over all these results. For the social science study, according to the literature, they were using GPT 3.5 to construct all the Silicon samples. Well, they have like 33 historical tasks according to 33 different subgroups from 2016. Well, they also have 33 tasks in 2020. So we use the historical tasks from 2016 to calibrate the prediction on 2020. And here is our result. If we target at the confidence of 85%, then you can see the orange interval, which is very tight, still doesn't cover the ground truth for all of the 33 tasks in 2020. But for the confidence interval that we derive, which is shown in the gray interval, it covers the ground truth, or it covers the feeling thermometer in 2020 by 97%. So this is a huge contrast between 97% coverage and 3% coverage. And this is all just gained by calibration based on the historical task in 2016. And in the Bradley-Terry score application, we in the data set, we have like 74 models, and we kind of like trying to mimic the scenario of when a new model release, we would only use the AutoRater to rate the battle between the new model and the model that already exists. And for the historical task, we will leave the model that we will try to predict out, and then construct the historical task based on the model that we already have. But like we apply the AutoRater to the model that we already have and infer about the Bradley-Terry score. And we aim at the confidence at level of 90%. And with our method, you can see that still our interval are much wider. But if we only naively construct the Bradley-Terry score based on the AutoRater ratings between the new model and the older model, the older pool of model that we have, then the coverage is just 75%. So it doesn't reach the 90% that we aim at. But if we use our own Bradley-Terry, we use our exchangeability to calibrate on the gap between the synthetic data and the real data, then the coverage would actually reach 100%, which would be much higher. So later on, we just think about, okay, if the confidence are actually much higher than 90%, what can we do? Can we also try to narrow down the Bradley-Terry score? So we apply our algorithm 4 instead, which targets at the finite sample. And here, the confidence interval is 3 times shorter, or 3 times narrower, and also it gives us a more confidence in the ranking based on the Bradley-Terry score. But still, we recover like 90% of the coverage for the Bradley-Terry score that are gonna be fitted based on the real ranking or real rating based on the human ratings. So by far, the two examples of AutoRater for Bradley-Terry score and also the social science are all focusing on the systematic bias between LLM and human and ratings versus human ratings and respondents versus human respondents. But if we think a little bit deeper about the math actually never asks whether your data come from LLM or not. So the method, the real value of the method is that it only needs 2 things: a gold standard dataset that you trust and a cheaper pool dataset that might be systematically biased relative to the gold dataset. So what actually causes the bias, either it's using a synthetic model, or either it's using a simulator, or either it's using an LLM, or either it's like in your prompt, or either it's just because of time, it's irrelevant. So based on that observation, I want to show an example that is work in progress associated with our work in Agent Leaderboard steerability score. So here the bias comes no longer from the LLM itself, but it comes from the time. And that is something that's really hard to overcome. So on the Agent Leaderboard, to give a more concrete context, there's one signal that's a little bit more special, which is the steerability signal. That it depicts the behavior of human choosing to resume the session. So it will be under the influence of human resuming the session or not. And that will only be settled or unfolds over days, but not hours. So this is a time that it cannot avoid if we only rely on human data. So if we want to focus ourselves at the 24-hour within a release of a new model, then the collected pool of data do have systematic bias, and the systematic bias is exactly brought out by this time dimension, but not by other dimension. And the volume, and the thing I want to emphasize over here is that the volume of data cannot fix it, because it's a maturization bias, but not a sample size problem. So even though we might collect more and more data on day 1, the data pool based on day 1 are still suffering from this like systematic bias according to the human behavior. So here we can see that the gold standard data is actually, we would, according to our observation, usually the steerability signal would be settled around like 3 days. So the gold standard data would be the settled day 3 signal, or even the settled 1 week signal, or like the 1 week data. While the biased pool is the pool of data that we collected on day 1. And on the right, there's a figure that shows how makes the bias a little bit more visible. Basically, it's like regressing the settled signal based on the signal collected on day one or the score collected on day one. And you can see that it's growing over time slowly, but it starts from the coefficients of like 0.6. But on the same time, the tension is that we all know that the day one read is very important, or the day one evaluation is very important. For the labs, they want to iterate on the evaluation the moment the model ships, or within 3 days when the models are released. Well, for the community, on the very first day when the model is released, they want to read the evaluation. They want to read how good does the model perform. Well, at the same time, on the other hand, we have observed from analysis that especially for the steerability signal, it needs around 3 days to settle. And if we only use the naive confidence interval derived from the day one data, which is the systematic biased one, then the coverage rate would only be 57%. But with our method that calibrated based on the exchangeability idea or task exchangeability assumption, we will again retrieve the 90% coverage. And here is how we do it. So the calibration part is the part that we have been iterating over the past 2 examples. But one thing that is a little bit new is that we first do a prediction and then we calibrate. So first, we kind of trained a very simple and coarse prediction model to map from the signal that we collected from day one, not only steerability signal, but also some other signal that would be useful to predict on the settled day 3 value of the steerability score. And then we measure the gaps between the settled score and the predicted score instead of the settled score and the naive synthetic score across the other launches. The other launches actually refer to the older models, or the models that we already observe and have collected data for our agent leaderboard. And then we just wrap around our confidence interval based on the gaps that are derived from the older model. So the fine print over here, and this is also my favorite part of it, is that in a more ideal scenario where train and test data set are IID, the gaps that we're going to observe across models would just be mean zero noise. So that is the ideal world. But the thing is, we never check that. We can never check that, and we never need that according to this framework. So the calibration would tell us more about how perfect was the synthetic data, or how perfect was the day one data. And the other thing about this framework, about this application, is that we're not even relying on the exchangeability between models, because some models might be stronger and some models might be weaker. But the thing is, the validity, or the validity only comes from the fact that the gap itself is exchangeable, or the time distribution shift is exchangeable across models. And that is a much weaker assumption than exchangeability between models. And here is our result. This is on the left, this is the interval that we derive. And on the right is the synthetic only confidence interval derived based on the day one data, which you can see that the naive coverage was only around 57%. And if you increase the amount of data and push the prediction line from 24-hour to day 2, from day 1 to day 2 to day 3, the coverage from the naive confidence interval will still be kept around below 80%. But with our method, the confidence interval coverage would actually grow from 88% to 91%. So our confidence interval derived on the left, as you can see, it's much higher, and also it's valid. It covers the truth. And in future work, we are going to test this framework from predict to calibrate, or predict to exchangeability on the new models. And that will be integrated into our work on the agent leaderboard. So just all of this work or like all of the application, we are always emphasizing one thing. Either it's exchangeability among models, exchangeability among historical tasks and recent tasks, or it's exchangeability among the gaps, the time shift observed on different models. Well, people may raise a further question, that is, what if the new task isn't quite exchangeable? What if we are actually hunting for a new task that is no longer symmetric to the older task? And the practical approach is maybe sometimes we don't even need the exchangeability assumption. And the approach that we give is to give historical tasks a relevant weight. So we can upweight the same model family, we can upweight the recent waves that are more relevant, or we can upweight the groups that are more similar, the population that are more similar, or we can upweight the tasks that are drawn from more similar contexts or similar topics while using the pure domain knowledge. And then our theory will be adapted to this kind of like weighted version exchangeability, where we just add a term of epsilon that will measure the distance from exchangeability. So under the perfect exchangeability, the epsilon will be equals to 0. But if the exchangeability are broken by some non-symmetric moves or non-symmetric rules, according to our domain knowledge, we'll use the epsilon to measure the distance from the new task to the older task, or the new task to the weighted historical task. So we will only need to control the epsilon, but the method that calibrates on the historical task will still be applicable to the new task. So I guess for now, it's already approaching the end of this talk, and we have go through the method, and we have go through all these empirical results, especially the one that are most exciting about on the agent leaderboards. And at the very end of this talk, I want all of us to zoom out a little bit for the last 2 minutes, because I do believe that what we did today is a simple or small instance of something that is much bigger. So for the people that are sitting in this room are very familiar about machine learning. And if we look into the history or like historical development of machine learning, it actually grew up inside the single task, where we were assuming that we have access to one data set coming from one underlying distribution. There were one mapping that we care about, and there are one test set. Well, all of this, like classical statistics, estimation, confidence validation, we're living inside that box, and it has served us well for, almost like half a century or even like a century. But currently, the general purpose AI broke the box, where one system now performs every task from math to coding and then to image generation. And it actually will includes more and more tasks that no dedicated data set was ever collected for. And I want to be clear about this, that this is not a temporary problem that will be solved by a better engineer. But this is actually the defining statistical condition of this era, where the data that you question, or like the data for the question that you care about, may no longer exist, but the data for 1,000 neighboring questions do exist. So the unit here is no longer a single data set, but the unit here is actually moving from data points or data sets to tasks or groups of data. So a century ago, the statisticians were asking, what can a sample of people tell me about the population of the people? Well, currently, what we ask is what a sample of tasks can tell us about the task in front of me today, or what a sample of tasks from the historical population can tell us about the task that I am gonna conquer or I'm gonna face, like in a new environment. And once you set the task itself as the unit, you need an assumption to play the role of IID that used to play the role amount for the data points. And I believe that exchangeability is the correct language for the task universe. And inference no longer lives within the task, it lives across the task. So that is the main takeaway for this methodology. And even more, before I set end to this talk, I want to leave one question hanging in this room. And the one question is actually sounds almost too simple to ask. That is, what is data? So in this room, in this company, we're interacting with data every day. We're drawing value from the data. We're drawing conclusion from the data. We are filtering out data based on their quality. But can anyone tell me what is data exactly? And how do we measure the quality of it? Well, I was thinking about this question, and my answer is actually I propose a decomposition to the data itself. I would propose a formula for the data as execution plus representation. So the execution is actually Y, or like the labeling for supervised learning, or it might be the policy for the reinforcement learning. Or given the prompt, what is the answer of the LM? Or like what is the answer? How does it perform on the coding problem? What is the proof that it proposed for the math problem? Those are all the execution, and it measures how well the answer is. And all the failures that we saw today, or like in the examples that we have, we are all measuring upon, how biased are the answers, or how biased are the labels, or how biased are the ratings. But another thing that we might be ignoring, or like we actually are paying more and more attention to, is the representation itself, which is the quality of the input X. How much of reality actually carries. And in the world that we are living in, where the AI model are iterating faster and faster, the execution point is saturating. More and more complex tasks are being solved like within just 1 month, and then more and more complex tasks are coming in, and all the benchmarks are actually saturating. So the execution might no longer be the difficulty, or might no longer be the challenge in the future. But instead, if we focus on the representation, it's not saturating at all. Because think about like what X is actually contains. It's used to be, a perfect pixel of images where we can tell what is dog and what is a cat. But now it might become a prompt. It might be a very vague prompt. It might be the demographic profile we would feed to the LLM as a social scientist. It might be the context we hand in to the model. It might be a very simple idea, a very vague idea when we started to coding for a very complex task. So more and more of the information and more of the gap between the data from the reality is actually hidden in the X itself. So if we go back to the kind of like silicon sample that we use for the social science, and imagine very simple, strongest possible case where the one day AGI might arise, then the execution might become perfect. And the question remains, does the demographic profile actually represent the person? Does the demographic profile, the features actually represent the human that are actually, answering the question in the real world? And did we actually include everything about the question that matters, or about the human that matters, or only the feature that we happen to be included in our prompt? So that gap of the data between the data, or like between the inference from reality, actually lives in X, but not in Y, not in the performance of F, or not in the strengths of F, or like the model itself. So no future model release will actually close the gap. And here we propose a methodology, or a fundamental language of exchangeability that will still be applicable to the world where the gap lives in X, but not in Y. And at the end, I would like to end the thoughts based on just one sentence. As the tools become more powerful, the people who use them becomes the decisive factor. And we need to measure the gap always between the reality and the data that we observe. So thank you all. That's my talk today.